So the first of our applications for double integrals is actually an application that it's old. It's an old kind of application. We knew how to do this in single variable calculus, but we're going to be reframing how we did it in single variable calculus in a different way. So one application for double integration is to compute the area of a region in the xy plane. And the way that that works as a double integral, because remember, double integrals, when we were introduced to them yesterday, they have the interpretation of volume, not the interpretation of area. And so if I want to use a double integral to compute an area, I need to figure out what volume is going to be numerically equal to the area that I'm trying to compute. So for example, in the activity we're about to do, we're given a region that's bounded by the curves y equals 1 minus x squared and y equals x minus 1. So if I want to describe this as a type 1 region, because y is equal to a function of x in both cases, this is going to be the most natural way to at least get started, then I would probably want my, upper function to be 1 minus x squared and my lower function to be x minus 1. So x minus 1 as my lower function, 1 minus x squared as my upper function. I'm not sure off the bat what my bounds on x are going to end up being, so let's just put these on the screen. And I think the intention here is that the intersection points of these graphs are going to define for us what the x range is going to be. And so my x is only going to go as far to the right as this intersection point of these two functions on the right side, which happens to be x equals 1. And it's going to go as far to the left as the intersection point of these functions on the left side, which ends up being x equals negative 2. So I think this is a little bit of a spoiler for the early part of this activity, because the early part would have had you, first of all, looking to find those intersection points, which we can do with algebra, just by setting these two functions equal to one another and solving for x. But you get x equals negative 2 and x equals positive 1. And so our type 1 description of this region would have y being bounded in between these two functions of x, and x ranging in between negative 2 and positive 1. So the question for us is, how can we use a double integral to find the area of this region? In single variable calculus, we found the area of this region just by integrating single variable function. And the single variable function we ended up integrating was just the difference, the upper function minus the lower function. Integrate that from x equals negative 2 to 1 according to your Calc 1 and 2 professor, and that will give you the area of this region. And they're not wrong. To look at this as a double integral, though, what we want to do is kind of imagine that what we're going to do is place another copy of this same picture exactly 1 unit above the xy plane, right? So that what we end up getting is a shape that looks just like this, whatever we call this lamina up here, a three-dimensional figure that looks just like this shape, but it has a thickness, it has a height equal to 1. And so the volume of that shape, that three-dimensional solid, is going to be equal to the area of this lamina multiplied by the height of our solid, which is equal to 1. And so that's how we secretly get the volume and the area to be numerically the same, is that what we end up doing is trying to find the volume underneath the horizontal plane z equals 1, and which lies above this region in the xy plane. So again, z equals 1, that's this horizontal plane, kind of defines, whatever thickness of 1 that we're looking for. And so then any region in the xy plane over which I integrate the function f of x and y is equal to 1 is going to give me a volume underneath this horizontal plane whose volume is numerically equal to the area of the region in the xy plane that we're trying to compute. And so the ultimate moral of this story is that we can compute the area of a region in the xy plane just by integrating over that region as a double integral the integrand that's 1. So this is why sometimes authors will use dA as the infinitesimal element for a double integral, because if I just integrate dA by itself over a region D, then the result of that integral is just the area of the region D. So that's why this element that belongs in the double integral before we go into coordinates, this element is often called dA. When we go into rectangular coordinates, dA ends up becoming dx times dy. But as we'll see in the next section, when we go into polar coordinates, we play with that a little bit because dA has a different expression in different coordinate systems. But in general, it just means this element of area, because if we integrate just it multiplied by 1, that volume that we get is numerically equal to the area of the region D. So your task in this first activity is to set up an iterated integral that would find the volume of this region D, and then go ahead and evaluate it to get the practice. Now, you will have the choice of whether to use a type 1 or a type 2 description for this. I've already spoiled a little bit the first part, which is probably using that type 1 description is the easiest to do. If we tried to do horizontal cross sections on this and make it a type 2 region, we would end up running into some trouble because one part of this figure, so the lower part, is going to have a different horizontal cross section. It's going to go in between the parabola and the line. But then once we get above the x-axis, it would go between one part of the parabola and another part of the parabola. The line doesn't participate at all. And so if we tried to do a type 2 description, we would have to break this region up into 2 pieces because it would have a different left and right hand function down here than it has up here. So that's another reason why the type 1 description is much more tractable for us, because we can have the same lower function and the same upper function for every single cross section that we would draw through this region. So I will give you the floor to work out the setup of the iterated integral that finds the area of this region, which is equal to the volume of the function 1 above this region, and then evaluate that integral. The setup, again, is the most important in any of these problems, but to get us more practice with iterated integrals that we were just introduced to yesterday, please also do part B, which asks you to do that evaluation. So using a double integral to compute an area it seems a little bit like, hitting a fly with a sledgehammer, right? We could have found this area in single variable calculus, but what's interesting, I think, is how quickly the double integral that you set up to find this area reproduces the technique and the strategy that you used in single variable calculus to compute the area between two curves, right? So you set up this region by tape measuring it as a type 1 region. So using these vertical cross sections, y runs between the lower function of x, which is x minus 1, and the upper function of x, which is 1 minus x squared. And then x runs from -2 to +1. And so your iterated integral looks like this one, right? X minus 1 to 1 minus x squared, -2 to 1, and your integrand is the function 1, so that the volume that you compute is numerically equal to the area of the base, which is the area we're looking for. And so when you do the first one of these iterated integrals, the first step where you integrate with respect to y, the first thing that pops out after that, because when you integrate 1, you get y, and then you evaluate y from x minus 1 to 1 minus x squared, and the result is 1 minus x squared minus x minus 1. This is exactly the upper function minus lower function integrated from -2 to 1 strategy that you would have used in single variable calculus if you were finding the area between these two curves. And so that is the reason that this strategy works, right? The reason that this works to compute an area is that right away it just gives us upper function minus lower function integrated from whatever our x bounds might happen to be. But of course, it also gives us the way to compute the area of a region in the xy plane, even if it's not being described as being bounded by two functions of x. If it's a type 2 described region where x is bounded between functions of y, we can still use this strategy. If it's a region we can describe in polar coordinates, as we'll do a little bit later on today, we can also use this same strategy by integrating the function 1 to find the area of that region. So that's the good news, is that this is going to give us flexibility to find the area of a region in the xy plane, no matter how we describe that region in coordinates.